Alright, so before we move on to trig, we're going to pause for one more topic related to the previous one. So in the last couple of videos we looked at exponential and logarithmic functions, and we saw that they had this inverse relationship between them where one function would cancel out the other. This is a special case of this general principle of an inverse function, which is something that we will have to talk about at some point in the course. So let me remind you how this generally works. You can't define inverses for any old function, only for certain special types of functions, and these are what are known as the one-to-one functions. So a function is one-to-one if it has this property that anytime you put different inputs in, you get different outputs, right? So as long as x1 and x2 are different values that you're putting into the function, you should expect that the y values coming out are different, right? And of course, this isn't true for any function. There are plenty of functions that are not one-to-one. For example, for a constant function, every input goes to the same output. So another way that you can rephrase this is you can say, well, if it did happen that two outputs were the same, so if f of x1 is equal to f of x2, that has to imply that, well, if the outputs were the same, then the inputs must also be the same. So a one-to-one function graphically is one where, so we know that for any function, so we know that, you know, if you have something, say, like this in your graph, right? One of the tests for a function is this vertical straight line test. So this would tell you, you know, the fact that you had this and this, you have two y values corresponding to an x value. This would tell you that it's not a function. And this is often called the vertical line test, vertical straight line test, right? Similarly, if you kind of do things the other way around, you can look at horizontal lines. So this property of being one-to-one would mean that if you had a graph which, say, went like this, that's perfectly fine. You can have a function that looks like that. That looks like a perfectly good polynomial function. But if you drew a horizontal line, you would find that there were several x values that gave you the same y value. And that would tell you that this is not well, it is a function, but it's not one-to-one. So a one-to-one function is going to be one where if you draw a horizontal line, it only cuts the graph once, right? So any horizontal line is going to cut the graph at most one time. Okay, so let's see some examples and play around and say, well, how would we actually demonstrate that that a certain function is one-to-one or is not one-to-one? Now, in the definition of being one-to-one, it's not stated explicitly. Well, I guess it is right here. These words, for any. Okay, so for any choice of 2 points in the domain, if I choose different inputs, I have to get different outputs. Or put another way, if I choose any 2 points in the domain, if the outputs come out to be the same, the inputs must also be the same. So the easiest way to test for one-to-one is to suppose you have two inputs that give you the same output, and then try to show that those inputs had to be the same. So if I look at question 1, right, I could say, well, let's suppose that f of x1 equals f of x2 for some x1 and x2. Well, what does that mean? That means that 2 times x1 plus 1, there's f of x1, would have to equal 2 times x2 plus 1. There's my f of x2. Well, if that's true, then I could subtract 1 from both sides. 2 times x1 would be equal to 2 times x2. And then I could divide both sides by 2. And x1 would be equal to x2. So anytime the outputs are the same, the inputs have to be the same. And that tells me that f is 1, 2, 1. Now, what about the next function, g of x? Is it going to be one-to-one or not? Well, g is not one-to-one And if I want to show that g is not one-to-one, I don't go with the same procedure that I used in the first one. So in the first one I was trying to establish that it is one-to-one, which means that for any choice of inputs, if the outputs are the same, the inputs had to be the same. To show that something is not one-to-one, I just have to find one example where different inputs give me the same output. And so I can simply do something like this. So this is what's called finding a counterexample. So I could say that since g of minus 1 is equal to 2 times minus 1 squared plus 1 equals 3, and g of 1 is 2 times 1 squared plus 1 equals 3, but of course 1, I think everyone will agree, 1 is not equal to minus 1. That means that g is not 1, 2, 1. And of course you could see that graphically if you were to try the horizontal straight line test. The graph is a parabola, and of course the horizontal line is going to hit the parabola in two places, not just one. And so you know that it can't be one-to-one. I'll leave the third one here as an exercise for you guys to try. I'll tell you in advance that it is a one-to-one function, and your argument is going to be pretty similar to the one I did for the first example here. Okay. So let's say somebody hands you a one-to-one function. How do you define the inverse? So the idea with the inverse function is that, the original function, you put in the x value and you get out a y value. The inverse takes that y value and tells you which x value it came from. And here's where you need that one-to-one property, because if you want the inverse to actually be a function, right, then when you put that y value in to your inverse function here, well, if it gets associated with more than one x value, you're not dealing with a function anymore, because each input can only go to one output. So this is where the one-to-one property comes in. If there were two different x values that gave me the same y, I would not be able to define an inverse that was actually a function. Okay. So here's this defining property, right? So if y equals f of x, for the inverse, we turn it around, we plug in y, and we get back the x value. We can also think in terms of these cancellation properties. Okay. So if I take f of x and I plug it into the inverse, I get back x. Or if I've calculated f inverse of y and I plug that into f, again, the two functions cancel out and give me back the original value. You can think of this as working very much the same way as how subtraction is the inverse for addition, or division is the inverse of multiplication. It's the same sort of idea with inverses, right? You're trying to undo something, right? Subtraction undoes addition, division undoes multiplication. So the inverse of a function undoes whatever the original function was. Okay. And we'll explore plenty of examples with inverses as we proceed through the class. One of the things that you might have seen if you saw inverses in your high school course is this graphical relationship between them. Here's the line y is equal to x. You'll notice that if you compare the original function to the inverse, you're sort of exchanging the roles of x and y, right? So for the original function, we know that y would be on the graph, because x is an input and y is an output. Over here, y is an input and x is an output, and that means that the point yx is on the graph, right? So one way to think about inverses is basically you take every point on the graph, you switch x and y, and that's going to give you a point on the graph of the inverse. So if the original function had a, maybe the, I don't know what it looks like, maybe this is your y equals f of x down here, then the inverse is going to be the mirror image of that, so it might look something like this. Okay, they're both reflected across this line, y equals x. So let's see how you figure this out. So here are a couple of examples. Now I told you earlier that this function f of x is one-to-one. I left it as an exercise for you to show that it is. Feel free to pause right now and confirm this. But I'm going to show you how to find an inverse. Okay, so how do I find the inverse? So we can do this. So let's suppose y equals f inverse of x. Well, we know what the definition tells us is that that means x has to equal f of y. But what is f of y? Well, we know how functions work. This function notation means whatever you put in the brackets there, you plug in where you see the x on the right hand side. So if I see here that, well, if I put x in, I should just put an x there, and that's how I do the function. The same thing works if I've got a y. So f of y is 1 over 1 plus y. Okay? So I know that x equals 1 over 1 plus y. What do I do with that? Well, what am I trying to find? I'm trying to find y. That's what I'm looking for. So what do I have to do? I got to solve for y. So let's multiply both sides by 1 plus y. So x times 1. X times 1 plus y is equal to 1. We'll just cross multiply. So I'm going to multiply through the brackets here. X plus x y is equal to 1. So x times y is equal to 1 minus x. And that means that y is going to look like 1 minus x over x. Okay. And one way to think, if you think about these as processes of undoing things, this sort of makes sense, right? So if you take x as your number, so what does f of x do? So f of x says you take a number, you add 1 to get a new number, and then you take the reciprocal of that new number. So if I was trying to sort of reverse my steps, how would I kind of reverse my steps if I was trying to kind of go back? Well, and by the way, notice that what this is, if I sort of simplify things here, I can divide term by term. This is 1 over x minus 1. So that's f inverse. So let's think about our steps. Step 1 was add 1. Step 2 was take the reciprocal. So if I want to reverse my steps, think about doing undo. You always, when you start undoing things, you start with the very last thing you did. So if the very last thing you did was take the reciprocal, I need to first undo that. So how do I undo reciprocal? Take the reciprocal again. So if I take x, the first thing I do is take a reciprocal. That undoes the reciprocal step. And then the next thing I need to do is undo is the adding 1. How do I undo that? Well, subtracting 1, of course. So we see that we have that rule. Take the reciprocal and subtract 1 is going to reverse the steps that we did with the original function. And one of the things that you might check that f inverse of f of x equals x. So there's a bit of algebra there, and it'll test your understanding of how function composition works. So it's a good exercise to work through and make sure that you can verify that that works out. Now, this second example is interesting. Here's my function. G of x is square root of x. Okay. Here's what the graph looks like. Okay. Y equals the square root of x, and I'm telling you that it's 1 to 1. Okay, you can confirm that it's 1 to 1 if you want. And so if it's 1 to 1, well, what's the inverse? So let's think about it. So suppose that so y equals g inverse of x. So that means that x should be equal to g of y, which is the square root of y. And well, that suggests that if I square both sides, y equals x squared. So does that mean that the inverse is x squared? Well, g inverse, sorry. Does that make sense? Well, here one of the things that you can check for yourself is that the inverse of an inverse gives you back the original function. So every inverse also has an inverse. So every inverse must be 1 to 1. But the x squared function, that's not 1 to 1. Right? We know that's not a 1 to 1 function. How could this possibly work? How could that be an inverse if it's not 1 to 1? Well, it is a 1 to 1 function. The difference is that it's not the full squaring function, because the full squaring function has range all real number, or sorry, has domain all real numbers. But remember that the domain of an inverse function is given by the range of the original function, and the range of the square root function consists of only values of x bigger than or equal to 0. So that means the domain for this G inverse here doesn't include the negative numbers. It only includes the values that are bigger than or equal to 0. And so if I were to plot the graph for G inverse, the graph actually is just 1/2 of that parabola, and that's why things work out. Okay, that's it for this one. We're going to move on to trig in the next video.